Exercise 23. Here we have two groups are given. We have to find the order of each group, that is the number of elements in each group, and we have to also find the order of every element in both the groups. So let's see the solution. So the first group is your Z12 or Z12. We know that the elements in this group are these 12 congruence classes. Which we know what they are. For example, this element consists of, it is a set of integers where we have precisely those integers that leave the remainder 2 when we divide them by 12. So they are of this form: 12m plus 2, where m varies over the set of integers. So like that, the other congruence classes also have their meaning. Hence, the order of this group is 12 because there are 12 elements. Now, next we have to find the order of every element. The first thing we notice is that the order of this zero congruence class, which is the identity element in this group, is 1. The identity element in any group has order 1. Why is that so? Because say you have a group G in which you consider the identity element E. G may itself be a finite group or infinite group. Whatever G is, it does not matter. The order of E is equal to 1 always. Why? That is because the first power of E is equal to E. And by our definition, the order of an element is the smallest positive exponent for which the corresponding power of the element equals the identity. So this is in fact the smallest positive integer itself. So that is why the order of E is 1. In particular, here, because of that reason, the order of this zero congruence class is 1. So we write like this. Next we come to this 1. Now note that in this group the binary operation is addition modulo 12. So we have to keep that in mind. It's not multiplication modulo 12. Note that if you calculate this thing, what is this actually? This is your integral power of the element 1 in our group Z12, and that power is this. In a general group, we have a notion of an integral power of an element where you can raise any element to an integer exponent and you have the corresponding power. Now, because our group is an additive group, this same thing is written like this. And you know what it means. It is your usual this usual sum, where 12 copies of this congruence class are there. So you can see that this becomes, by the definition of addition modulo 12, equal to the congruence class of 12, congruence class containing 12, but because the modulus of this, the modulus you have here is 12 itself, and 12 leaves the remainder 0 when divided by 12. So this is equal to 0, which is the identity element of the group. Also, for any integer m satisfying this, that is, m is a positive integer and strictly less than 12, we have m1 equal to m. This, however, is not equal to the identity element, the zero congruence class. Do you see why? That is because for this to happen, we should have m congruent to 0 mod 12, or in other words, that 12 has to divide m. That, however, is not possible because m is strictly less than 12 and it is a positive integer. So how can 12 divide m? So that is why this will never become equal to 0. So 12 is the smallest positive integer m, or say n, for which n times 1, or in other words, the nth power of this congruence class is the identity, and n is the 12 is the smallest such n, that is, we have this, and that is why the order of 1 is 12, order of the congruence class 1 is 12. Hence, the order of the congruence class 1 is 12. One can similarly calculate these other orders. The order of the congruence class 2 is 6. The order of this congruence class is 4. The order of 4 is 3. The order of 5 is 12, just like 1. Now, one can in fact guess this order by arguing like this. For example, how does one know that this order is 12? Does one have to go through all these powers as you vary m from 1 through 12? Actually, that is not needed. you want an m, a positive integer m for which this happens, no? And because our group is additive, this means this actually means this itself. That is, we are operating m copies of this congruence class, which is equivalent to this, the congruence class containing the integer 5m modulo 12 is equal to the 0 congruence class modulo 12. If and only if 5m is congruent to 0 mod 12, or if I go one step ahead and write this, okay, so we have this. Now note that 5 is a prime number and it does not divide 12, so 5 and 12 are relatively prime. So by a previous result on divisibility of integers, then this would be equivalent to 12 dividing m. In this divisibility, 12 has nothing to do with 5 because it does not have any factor common with 5 other than 1. There is no other positive common factor. So its greatest common divisor is 1, that is, they are relatively prime. In fact, you can write, since the greatest common divisor of 5 and 12 is 1. That is why these two divisibility relations are equivalent. Now 12 has to, if this has to happen, then 12 has to divide m, and conversely, if 12 divides m, then this will happen. So what is the smallest positive m? Then in this situation, the smallest positive m thus has to be equal to 12 itself, and that is why the order of this element is 12. You can argue like this itself for the other elements to calculate the orders of the other elements. Let me just keep this calculation for now, and let me continue writing the orders of the other elements here on this side. And because we want to calculate this also after this, so let's just see what it is. Z2 cross Z4. Okay. In many of these solutions, I will be somewhat sketchy in writing the solution, and I will not write the actual formal solution in many this type of solutions which involve actual calculations. So I ask you to write the formal solutions, like how you would write in an examination. So this is 12, then like that the order of the congruence class 6 will be 2, this is again 12, what will this one be? This one will be 8. Okay, so 8 times 2 is 16, 8 times 3 is 24. 16 is not the congruence class, 16 is not the congruence class 0, but 3 times 8 is 24, and the congruence class 24 is equal to the congruence class 0. So this is 3. Then 9. 18, 27, okay, 36, so this is 4. then 10. You can quickly go through these steps. For example, here, if you have 10 here in place of 5, you would then need this. That is, if you cancel the common factor, which is 2, you have this. And 6 and 5 are relatively prime, so 6 has to divide m. So that means n must be 6. The smallest positive n is 6. So this is 6. And finally, this is 12. So we have calculated the orders of all the elements of this group Z12. We have calculated means actually we haven't calculated. These are only guesses. Okay, you have to, each such conclusion comes from some such calculation, okay, which actually you have to go through. So this is the first one, and then the second one. This time we have Z2 cross Z4. So its elements are ordered pairs of group elements. And what now I am going to write, I have to explain the notation a little bit. One zero, one one, one two, and 1 3. What needs to be explained about this? We just need to make something sure that, I mean, there should be no doubt about the difference between this 0 and this 0. They are not the same thing. Although we are using the same symbol to denote these two congruence classes, but you can clearly understand that they are different objects. Because this 0, this congruence class, 0 within square brackets, is coming from Z2, it's the congruence class modulo 2, that is, it consists of integers of this form, that is, it is the set of even integers. However, this 0 is different. This is the second 0. It is the set of those integers which leave the remainder 0 when divided by 4. So those integers look like this. They are multiples of 4. And these are two different subsets of the set of integers. But because there is no chance of confusion, since we know where the first coordinate elements are coming from and where the second coordinate elements are coming from, so we decide to use the same notation. If you want to really distinguish between these two things, for example, here also, you can write something like this. Say you can provide these notations with these extra symbols, suffixes indicating the moduli. The first modulus is 2, the second modulus is 4. You can devise some such notation. But we don't actually need anything like that, because and the reason is that we will not mix up elements. For example, we will have no occasion where we have to, for example, what can I say, somehow include both these congruence classes 1 and 1 in the same calculation. So there will be no chance of confusion. That's why we use the same notation. Now here we can see that this group has 8 elements, so its order is 8. Thus the order of Z2 cross Z4 is 8. Next comes the task of calculating the orders of the elements. This element you already know is the identity element in this group. So its order is going to be 1. And without writing any elaborate calculation, I am just simply going to mention the orders of the other elements. You have to actually go through the calculations. You have to show all those calculations in the solution itself. Next, the order of this element 0, 1 is, because this 1 is coming from C4 and its order is 4, so this is 4. Next, 0, 2 its order is 2. Next, (0, 3). The order of 3 in this second group is 4. So this is 4. Now we come to those elements which have the first coordinate congruence class 1. Its order will be 2. Then the next one 1, 1. The order of this one is 2 in the first group, but the order of this one in the second group is 4. So this has to be 4. This one has order 2 and this one also has order 2. So that is why this has order 2. Next, this one has order 4, so 2 is not enough, it has to be 4. So these are the orders of all the elements in this second group. Now the next exercise is also like this. I think I could use some ink already. Find the order of every element of each group. Every element of each group. Is the group cyclic? That also we have to figure out. And what else? If so, list all its generators. So these are the two groups now. The first one is U14 and the second one is our familiar non-abelian group S3, the symmetric group of degree 3. Now this time we don't have to find the order of each group, but we have to find the orders of the elements. So let us look at U14 first. We know that U14, recall what the group U14 is. U14 is also a group whose elements are congruence classes. Now here also the modulus is 14. But unlike Z14, U14 has in it those congruence classes where the representative integers are relatively prime to 14 and the binary operation in this group is multiplication modulo 14, not addition modulo 14. And not just congruence classes like that, what I said just now, non-zero congruence classes. So the first one is 1 because the representative integer 1 is relatively prime to 14, and you can see why every integer in this congruence class will be relatively prime to 14. Then 2 is not relatively prime to 14. The GCD of 2 and 14 is 2, it's not 1. 3 is. 4 is not. So all the even integers have to be discarded. So the next one is 5, but then you cannot take 7 because the GCD of 7 and 14 is 7. You cannot take 6. I mean, of course you cannot take 6 and then you cannot take 7, you cannot take 8, but you can take 9. What next? 10 is not an option. 11. 12 is not an option. 13. In order to see if you have got all the elements, you just calculate. If you are familiar with Euler's totient function or Euler's phi function, you calculate this value. It gives you the number of positive integers less than 14 and relatively prime to 14. And the rule for calculating this is you take the number and multiply it with these things. What are these 2 and 7? They are the primes in the prime factorization of 14. So if you know the prime factorization, you can calculate the phi value quickly like this. So you can see that this becomes 1 over 2 and this one becomes 6 over 7. So if you cancel 2, 7 and 14, you are left with 6. 1, 2, 3, 4, 5, 6. So yes, these are all the elements in this group, and the binary operation is multiplication modulo 14. Okay, so let us now look at the orders. One can, now here also I am not going to do the calculations, I will just simply write the orders. One can calculate, the elaborate calculations are left to you. The order of the congruence class 1 is 1. Now in this group, this is the identity element because our operation is multiplication modulo 14. The order of 3 is, so we are doing multiplication modulo 14. Order of 3 turns out to be equal to 6. What this means is that, let me at least tell you what this means. This means that this equation is true and 6 is the smallest exponent for which this equation will be true. Translating this in terms of congruence, we will get this. 1 modulo 14. And further translating this congruence to its actual meaning, it means that 14 divides 3 to the power 6 minus 1. Okay, and 6 is the smallest positive integer for which these things happen. Like that, the other orders can be calculated. Now here you have to of course do somewhat much more calculation than the previous exercise. If you want, you can use a handheld calculator. What you do in the calculator, you in your if you have your Android phone itself, in that calculator, in the calculator application, you form a calculation like this: 3 times m, I mean 3 to the power m minus 1 divided by 14. If you put m equal to 0, then of course you get an integer, but we are not considering 0 values of m. For us, m is a positive integer. We are trying to find the smallest m for which this will be an integer. So if you type this thing in, if you give this input, you will see that the output already appears in the calculator app. So you don't actually have to press enter or equality key, because the moment you press that, this input is gone. So you can just look at this and see whether you are getting an integer or not. For all these values, whether you put 1 or 2 or 3 or 4 or 5, you will see that the output, you can see here, none of them is an integer, but the moment you put 6, you get an integer. So that means this is equal to 6. So that way you can save time. Or if you really like to do calculations by hand, so be it. You can go through the calculations. Next, the order of the congruence class 5 also turns out to be 6. And this turns out to be 3. since these are things I am just simply going on writing, so it's your job to actually see whether what I am writing is in fact true. This turns out to be 2. Oh, okay, do we have 10? No, we won't have 10. We will have 11 and 13. This is 3, this is not 2, and the next one is, it turns out to be 2. 166332. 166332. Okay. So now next we have to say whether this group is cyclic. It is cyclic. Why? Because we have elements of order 6 which is equal to the number of elements in the group. So those elements which have the full possible order, which equals the order of the group, they will generate the whole group, in the sense that every other element, and in fact the element itself also, all of these are powers of the element, sub-power of the element. Since there are elements of order 6 which equals the order of the group itself, the group is cyclic. And the elements whose orders are equal to 6, they are precisely the generators. The generators are 2 elements of order 6, 3 and 5. What this means is that if you start looking at the powers of this congruence class, say you look at these powers, four and 5, you will see that you get all these elements. Similarly, if you look at the powers of 5, congruence class 5, again you will get all these elements, maybe in some different order. So both of them generate the group, and hence the group is cyclic. Next, we come to the symmetric group of degree 3. Here, somewhat surprisingly, although this group is non-abelian and the previous one U14 is abelian, the calculations are somewhat easier than this one. Now because we are going to talk about S3, so we need to again give names to the elements. I think in a previous exercise, when we were going through some exercises on permutation groups, I already gave them some names, but I forgot those things. So anyway, let's just again give them some names. We know, so now this is 2. We know that S3 has these elements. The first one is of course the identity permutation 1, 2, 3. The second one, it does not really matter which I call the second one and which I call the first one, but let's just list them the way they have been listed in the text. 1 2 3 1 3 2. Then sigma 3 is it 2 1 3? Yes. Sigma 4 is 2 3 1. Then sigma 5. The main reason we are naming them is because when we write their orders, that time if we don't give them names, we will again have to write this somewhat big symbols. Otherwise, how can you say whose order is what? So this one is 3 1 2. 3 2 1. One can calculate that. Now in this case, the calculation I already said is easier than these calculations. You will see why. That the order of sigma 1 first of all is 1, because that is the identity element. Then the order of sigma 2. Sigma 2 interchanges two symbols, 2 and 3. It takes 2 to 3 and 3 to 2, and it does not affect 1. So you can imagine that when you calculate sigma 2 square, first it will take 2 to 3 and then again it will take that 3 to 2. So that means 2 is not changed by sigma 2 square. Similarly, 3 is also not changed. 3 will first be sent to 2 by sigma 2, and that 2 will again be sent by sigma 2 to 3. So 3 goes to 3, and 1 is already unchanged. So applying sigma 2 twice on it will have no effect whatsoever. So that is why when you calculate sigma 2 square, you get the identity element sigma 1. And sigma 2 itself is not identity, so its first power is not identity, but the second power is identity. So by the definition of order, this is equal to 2. Then the order of sigma 3. Sigma 3 interchanges 1 and 2. It takes 1 to 2, 2 to 1. So by similar arguments, this also has order 2. What about sigma 4? Now sigma 4 does not actually interchange just two symbols, it changes everything. 1 goes to 2, 2 goes to 3, 3 goes to 1. But you can see, if you look carefully, its order will be 3. You have to apply sigma 4 to any of these three symbols, 1, 2 or 3 times in order to get the symbol back. For example, if you are applying sigma 4 3 times to 1, the first time 1 is taken to 2, again you apply sigma 4, that 2 is taken to 3, and then again you apply on 3, that 3 is taken to 1. So 1 goes to 1. Similarly, 2 goes to 2 and 3 goes to 3. And you have to apply sigma 4 at least 3 times in order to get the same things back. So that is why its order is 3. Next, sigma 5. 1 to 3, 3 to 2, 2 to 1. So it's also like sigma 4. And here also you can easily see that its order is 3. Sigma 6, however, is again it interchanges two symbols 1 and 3. So its order is 2. Now note that unlike this one U14, here the orders are quite small, and in fact none of them is equal to the order of the group, which is 6. There are 6 elements in S3. So no element alone has the power to generate the whole group, and that is why this group is not cyclic, since the orders of all the elements are less than 6, which is the order of S3. So S3 is not a cyclic group. So no question of listing its generators, because there is none. And anyway you can, in fact there is no need to find the orders in order to say that it is not cyclic. You can argue somewhat differently like this. Every cyclic group, because of the very nature of cyclicity or cyclicness, whatever you want to call it, is abelian. That is, every cyclic group is abelian. But we know that S3 is non-abelian, so it cannot be cyclic. So that way also you can just simply, without doing anything else, just simply using the fact that S3 is non-abelian, you can say that it cannot be cyclic. So here this solution ends. Next, let G this be a cyclic group of order 20. Find the orders of these elements: AQ, A to the power 12, and A to the power 15. Now here you can use one result from the text. It is your corollary 3.232. Let M be a positive integer such that the corresponding power of AQ is equal to the identity, because we want to calculate the order of AQ, so naturally we will look at this equation. Then (3m) is equal to identity. What have we done here? Here we have used one of the laws of exponents, or one of the rules of exponents. You see in this section that if you take any group element A from some group and say m and n are integers, then you will see there is one result which is not proved in the text, which says that these usual rules of exponents with which we are familiar from our experience with real numbers, for example, continue to be true in general groups. It is this one that we have used here. This is equal to this. And now, from this last equation, we can conclude something using this corollary. What does that corollary say? It says that if some power of A gives you the identity and you already know the order of A, then the order of A has to divide that exponent. The exponent will be divisible by the order. Now here it's given that G is a cyclic group generated by A and G has order 20. So that means the element A itself must have order 20. So by this corollary we get this. 20 divides 3m. Now since and 3 are relatively prime, this divisibility is equivalent to that other divisibility, that 20 has to divide m itself. In this division, 20 has nothing to do with 3. This is equal to 1. 20 has to divide m. So what is the smallest value of m for which this thing is true? Clearly 20, smallest positive value. Thus the smallest positive, because we have already taken m to be positive, we need not mention it once more. The smallest value of m is m equal to 20. That is, the order of a cube is 20. One can similarly calculate these other orders. Order of a to the power 12 turns out to be 5, and the order of a to the power 15 turns out to be 4. Now these are things you have to argue and justify like this. Now say you complete these parts, then I want you to do something else. You go to corollary 3.2. If I am remembering it correctly, I didn't see this section properly. This is not the only result that this corollary says. I mean, its statement does not just have this part, but it has another part. Using that another part, you can in fact calculate these orders much more quickly, much more easily. So you try to think of that, how one can calculate using corollary 3.2, the second part of this corollary, these orders much more quickly. In fact, one won't have to go through all this hassle of writing so many things. It will be almost instant. But anyway, so this is your solution. So that means there will be a quicker and much smaller solution to this exercise. Now the next one is actually those rules of exponents that I mentioned here. It is simply prove theorem 3.6, whose content is just those rules of exponent. Now here I actually have proved it twice. Once in the group theory videos on Herstein's topics in algebra, and once in the videos of exercises by Galilean's algebra. So if you want, you can go to those videos and see the proof, or you try it yourself. So it's like a homework. In the next Lee video, I will do it. Okay, so for now, I leave this thing to you as a homework. It is somewhat theoretical. If you do not manage to find in those videos where we have this thing done, in fact, actually I went through those videos and I did not find myself. I wasn't able to find it. It is there somewhere, but I have lost it. There are so many parts. So you try to do it yourself. So we move on. And if you somehow do not manage to find it anywhere, and you are also not able to figure out how to do the proof, you just try this. You have to prove this thing, right? These two equations. Where n and m are any integers. So they can be, any one of them can be negative also, or both of them can be negative also. So first what you do, you try to argue that these equations are actually trivially true if at least one of these two integers is 0. If n is 0 and m is any integer, then it is trivially true. If m is 0 then and n is any integer, then also it is trivially true. This one is also trivially true. Then, so that means you can assume that none of them is 0. Then there are cases depending on the signs of n and m. If both n and m are positive, that is one case. If exactly one of them is negative, that gives you two cases. And there is that other case where both of them are negative, and these cases have to be treated separately. So what first you have to do, you consider the case where both n and m are positive. Now in this case, to prove these things, you have to argue by induction. In what way? There are two positive integers here. So what will you do in induction? You have to keep one of them arbitrary but fixed and induct on the other. Which one I won't say. Here their status is somewhat symmetrical. But here, however, they have a quite different status. Here n is inside and outside you have m. So you try to figure out based on which one becomes convenient for you, that which one should be used for induction. Now once you prove this case, then the other cases will follow from this, and the definition of a to the power n, where n is a negative integer. Okay, so you try to go through this and see what you get. In the next video, I will do it, or I will tell you where to look, because by then I hopefully will have found the thing done in my videos somewhere. So the next one is this: let A belong to G and B belong to H, where G and H are of course groups. That hasn't been mentioned explicitly, but we can understand. Suppose that the order of A is 12. In the group G, A has order 12, and in the group H, B has order 18, say. Find the order of the ordered pair A comma B in this product group G Cartesian product H. Whenever we are asked to find the order of an element in a group, you have to always, if you don't know anything in the beginning, you have to always go to that equation which is there in the definition of the order of an element. That is, the element, some power of the element is equal to the identity, where the exponent in the power is a positive integer. So we start like that. Let M be a positive integer such that the mth power of A comma B is equal to the identity element of this group G cross H. Now, just for the sake of, for once, for the sake of distinguishing the identity elements in G and H, because in general G and H are different groups, let's write like this: E suffix G is the identity element in G, and this is the identity element in H. Then, so because m is a positive integer, so by the definition of the binary operation in this group, this ordered pair will be equal to this. You can convince yourself that this is true by taking some small values of m, or you can rigorously prove this fact, which is very easy, by induction on m. Hence, by the definition of equality of two ordered pairs are equal if and only if their corresponding coordinates are equal. So we must have this and this. So by corollary 3(2), when you have an equation like this and you know the order of A, it has to divide the exponent. That's what this corollary, part 1 of this corollary says. So the order of A is given to be 12, so 12 has to divide M. Similarly, the order of B is given to be 18, so 18 has to also divide M. Now 12 divides M and 18 divides M, so M is a common multiple of 12 and 18. Thus, the least common multiple of 12 and 18 also has to divide M, because that's a property of least common multiples. LCM of 12 and 18, which turns out to be equal to 6. Oh, what the hell am I writing? How can LCM be 6? GCD is 6. LCM will be what? Product of these two divided by the GCD. So it is 36. That also has to divide M. So what is the least possible value of M? 36. So, and that is why we can directly write the order of this ordered pair in the product group is 36. So the 36th power of A comma B is the identity element here, and no smaller power equals the identity element. And you can pretty much understand why that happens, because when you raise this ordered pair to the 36th power, that 36 will come down over both A and B, and then you should get in the coordinates you should get the corresponding identity elements EG and EH. So whatever exponent here you have over A, that should be a multiple of the order of A, that is 12, and like that, because then only using the rule of exponent, for example here, if you raise this to the 36th power, what will you get? But 36 is 3 times 12, so you can write this like this, and also this is 18 times 2, so you do get the identity elements EG and EH here, and that's why you get this. However, why is it the least common multiple? Because it has to be a common multiple in order for this to happen, because that is the only way of getting EG and EH. At the same time, it has to be the least positive integer. That's why the least common multiple. Okay, that is why the LCM turns out to be the order. Next, let A and B be elements of odd order in a group. This one is interesting. B elements of odd order in a group. We have some group from where the elements A and B are coming, and they both have odd orders. Show that A square and B square commute if and only if A and B commute. We have to first show this. Also show that this does not have to hold if A and B have even order. Okay. It's an if and only if statement, so we have to prove two things. It is given that the orders of A and B are odd. Now if A and B commute, that is if AB is equal to BA, then A square and B square also commute, that is A square B square will be equal to B square A square. Let us first prove this. First, assume that A and B commute. Instead of writing that in words, we can write what that means actually, that AB is equal to BA. Then A square B square, A square B square is just simply this, no? A B B. Now first of all, this in place of this middle AB you can write BA, so you get A BA and then B. Then in place of these ABs AB AB you can write BA BA, and then again this in place of this middle AB. Oh, it was a big lightning. Anyway, so in place of this middle AB you can then write, now the power will go, again BA, so B BA A. In place of this middle AB we have written BA, but this is B square A square, so A square and B square commute. And in proving this, that A and B commute implies A square and B square commute, in order to prove this we did not have to use the fact that A and B have odd orders, but now we will need to use that fact. And in the course of these writing these equalities, these equations, we just simply used the fact that the binary operation in the group is associative, so we did not bother putting brackets like this, because it does not matter in what way we bracket these products, they are going to give us the same element. Conversely, now our assumption will be that A square and B square commute. Now we have to prove that A and B commute, and somehow in this proof we have to use the fact that A and B have odd orders. For the sake of simplicity, we will consider their orders. I mean, we will denote them by some symbol. Conversely, assume that A and B commute. let the order of A be equal to 2k plus 1, because it's given that the order is odd, and the order of B is equal to 2l plus 1, say, where k and l are non-negative integers. Non-negative and not necessarily positive. Why? That is because we are allowing the possibility for these elements, any one of them or both of them, to also have order 1, because 1 is an odd integer too. Then what is a to the power 2k? A to the power 2k then will be A inverse, because A to the power 2k plus 1 is identity. So if you multiply on both sides by A inverse and use the rules of exponents, you will get A to the power 2k on the left side, and on the right side you will have A inverse. Similarly, B to the power 2l is B inverse. Now, from this equation we get something like this: b square equal to a to the power minus 2 b square a square. You pre-multiply on both sides by a to the power minus 2, use the rules of exponents and everything, you will get this. Now, the peculiarity of this equation is that it can be used in itself. That is, you look carefully, b square is a to the power minus 2 b square a square. Now I can put that value here inside this middle b square. That is, in place of this b square I can again write and then using the rules of exponents I have this. If I do it once more, I will have this. That is, let me just show how we are getting these things. Now this becomes minus 6 b square a to the power 6. Now if you continue going like this, eventually you will reach a stage. Do you see the pattern? 2 times 1, 2 times 2, 2 times 3. So at some stage you will get 2 times L, or okay, I need K here because that's what we have with A. So at some stage we will get 2 times K b square a to the power 2k, and now this equation can be used because a to the power 2k is A inverse, a to the power minus 2k will be A, and b square, this one is A inverse. That is, we have obtained this: b square is equal to a b square A inverse, which implies, now if you post multiply both sides, post multiply means you multiply both sides from the right hand side by A, you get b square A here, and here A and A inverse they cancel out and you have AB square. and that in turn would imply next we will work with B. Okay, so this implies A is equal to b to the power minus 2a b square. Now we can carry out a similar procedure now with this equation. So for example, in our first step we will have this, which gives us b to the power minus 4a b to the power 4, and then again if you continue you will eventually reach this thing. And that will be equal to what? B to the power 12 is B inverse, so this is B, this is A, this is B inverse. We thus have A equal to BA B inverse, i.e. now post multiply both sides by B, you get AB equal to BA. So that's why A and B also commute. Oh, okay. Solution is not over yet. We have to also show that this is not necessarily true if the elements A and B have even order. And for that we look at this in our familiar group S3. The permutations one, two, three, 2, 1, 3, and say 1, 2, 3, 1, 3, 2 have order 2 both. We have already seen in that calculation when we were calculating the orders of the elements of S3 that these are permutations with interchange 2 symbols. So each one of them has order 2. So both of them have even order. Note that their squares commute. Why do their squares commute? It is because their squares are equal to the identity element. So both these sides are equal to the identity. In fact, all these 4 elements become, we actually have 2 elements, so they all become equal to identity. So here the equation is trivial. So A square and B square commute, but A and B do not commute. Let us do that calculation here. 1, 2, 3. I think I need more ink. Two, 1, 3. And the other one is 1, 3, 2. Recalling how we calculate this type of product, we have to start from here and then go to this one. 1 goes to 1 and that one goes to 2. So 1 goes to 2. 2 to 3, 3 to 3. So 2 to 3, and this one of course will be 1. 3 to 2, 2 to 1. So 3 to 1. And that is not equal to this other product 1, 3, 2, 2, 1, 3. 1 to 2, 2 to 3, 1 to 3, 2 to 1, 1 to 1, 2 to 1. So this will be 2, 3 to 3, 3 to 2, yes. So they are not equal because this function takes 1 to 2, whereas this permutation or function takes 1 to 3. So a square b square is equal to b square a square, but ab is not equal to ba. So if the orders are even, then it's not necessary that we have that result, what has been stated here. And now the solution is over. Next, let A and B be elements of a group show that the following pairs of elements have the same order. And what are the pairs of elements? The first pair is A and A inverse, and the second pair is AB and BA. Keep in mind that although in the exercises we have seen so far here, we have been dealing with only elements of finite order, but that's not the only type of elements in a group. A group may have elements of infinite order. So here, since it's not explicitly said, or in fact that is not given here, that these elements A and B actually have finite order, so that possibility of them being of infinite order is there. So we have to take that into account. In the first one, we have to prove that the order of A is the same as the order of A inverse. What that really means is this: If A is of infinite order, then A inverse also should have infinite order. And if A has finite order, then A inverse also has finite order and the same order as A. Okay, so let us first consider the infinite order case. Assume first that A has infinite order. What that means is that if you look at powers of A of this form where m is any positive integer, you will never get identity. So there is no m for which this equation is true. That's when we say that A has infinite order. And a necessary condition for that to happen in a group is that the group itself must be infinite. Now we need to prove first that A inverse also has infinite order. To the contrary, suppose that it has finite order. Suppose A inverse has finite order k. That means k is some positive integer which is the order of A inverse. Then the kth power of A inverse is equal to the identity. This implies by the one of the two rules of exponents that the inverse of the kth power is also equal to the identity, because this will be a to the power minus k, which is also equal to this by the rule of exponent, the second one. And hence a to the power k, which by one of the elementary group theoretic laws is the inverse of its own inverse, is also equal to the identity. This, however, is a contradiction because it says that A has finite order. Why? Because we have found a positive integer k such that the kth power of A equals identity. So the order of A is finite and is less than or equal to k, which directly contradicts our assumption. This contradicts the assumption that A has infinite order. So our supposition is wrong. And you don't need to write anything else. Supposition is wrong means A inverse cannot have finite order. It also must have infinite order. Next, next we look at the case where A has finite order. A has say some positive integer m. Then A inverse to the power m. By the rules of exponent, this is a to the power m inverse. Now because m is the order of a, this power equals identity. Identity inverse is identity. So that means the mth power of a inverse equals identity. This does not all by itself prove that the order of A inverse is m. It only proves that the order of A inverse is finite and less than or equal to m. Who knows, maybe a smaller power of A inverse also becomes identity. So now we suppose that. Now suppose this is equal to identity for some positive integer n less than m, then this is also equal to identity, because by the rule of exponent this will be equal to this, and both of them are equal to a to the power minus n, which implies this calculation is just like this one, but this is a contradiction. This is a contradiction since n is less than m, which is the order of a, and at the same time let us also mention that n is a positive integer according to our supposition. Why is this a contradiction? Because the statement that the order of a is m means m is the smallest positive integer such that a to the power m is identity. But here we have found an even smaller positive integer n than m, for which a to the power n is identity. So that cannot be true. And this contradiction arises from our supposition. So the last supposition is wrong. That means no smaller power of A inverse than A inverse to the power m can be identity. So now we can say for sure that m is also the order of A inverse. Which is the same as the order of A. So this is the first part. Now in the second part we have to prove that AB and BA have the same order, that is we have to prove this. Here also that finite infinite that thing will come. So I am not going to do it, I leave that to you. You have to prove that if AB has infinite order, then BA also has infinite order. And the finite case also I am leaving, but with this hint. Note that AB and BA are actually conjugates. You can write AB as a conjugate of BA in this way. A inverse, no, okay. AB has to be written as a conjugate of BA. So let me just first write BA, and I want this A to vanish. So that means I write one A inverse here, and here I want an A. So note that AB is the conjugate of BA. Now what does this have to do with their order? To see what, you look at theorem 3.6. This theorem says that any element and its conjugate have the same order. So with these things, you try to complete this solution. Next, let a K be a finite abelian group. It is finite, we can see from this description of G, but it is also abelian. Show that this particular element, which is the product of all the elements of this group, has order either 1 or 2. Here also I will give you the hint. When you take the product, okay, let me first ask you to look at this thing, the square of this product. The square of this product by definition is the product of the elements but you can use the fact that G is abelian to change the order of these elements in any manner you want. Why shall we do that? What is the benefit of doing such a thing? Note that because all the elements of the group are appearing here in each product, you in fact can write this product like this. Now the way I have written it here, it may look a little confusing. It seems like I have written A1 inverse in place of A1, A2 inverse in place of A2, and so on. But no, that is not the thing. You see, every element has an inverse. That inverse may or may not be equal to the element. We don't bother about that. The fact that all the elements are actually appearing here tells us that the inverse of A1 is here in this product somewhere. In this product, forget about this one for the moment, just concentrate on this product only. The inverse of A1 is here. That A1 inverse may be equal to A1, it may be equal to something else, some other AI. It does not matter, it is there. So you can write, you will find A1 inverse here somewhere. Now we can bring that A1 inverse in the front of the product because the group is abelian, we can change the order in any manner we want. So we decide to write A1 inverse here. So like that, you can write the inverses of all the elements, and conveniently I have chosen this order to write again, rearrange the things in the product in such a manner that the inverses now appear like this. Now if you continue to find inverses of all these elements, okay, so you have written the inverses. Will there be a problem? In what sense? Shall we leave something out? Will there be an element in this product that is not the inverse of any of these elements? No, that cannot happen, because if you have an AJ here, that AJ appears as the inverse of something, and that thing is AJ inverse, because AJ inverse is AJ. So just like you can find the inverses of all the elements here, conversely every element in fact appears as the inverse of something, and that something is unique. So there is a one-to-one correspondence between the elements and their inverses. So you can write this product also like this. The order I have been able to change, and I have been able to freely choose the order as I like. That is because the group is abelian. And now, using the fact again that the group is abelian, I can write this entire thing like this. Each one of them is identity, so you get identity. So that means this square of the ultimate product of all the elements in the group, equals identity. Now in carrying out these calculations, you have to write all those justifications. But then what? Because the square of this element is identity, corollary 3(2) tells you what? That the order of this base element, that is this product, the order of this product divides 2. Now because the order of any element by definition is a positive integer and 2 is a prime number, so there are only 2 possibilities for this order. That is, this order can either be 1 or 2, because those are the only positive divisors of 2. As order either 1 or 2. So that's how you get the solution. Next, show that it is possible for an abelian group to have exactly 3 elements. For an abelian group to have exactly 3 elements of order 2, but not exactly 4 elements of order 2. Now, what is the idea here in this exercise? For the first part, to show that we can have a group with exactly 3 elements of order 2, we actually have to produce an example. And for the second part, that there can never be an abelian group with exactly 4 elements of order 2, we have to provide some sort of argument. So here also you will write the elaborate solution. I will just give you the hint. You look at this group. You know what its elements are. In this case, unlike the first exercise, the 2 congruence classes actually are the same thing. You can argue just like how we did in the first exercise to show that these 3 elements have order 2 each, and this one being the identity, of course, have order 1. So this group, and this is of course an abelian group, it's a direct product of 2 abelian groups. So there are exactly 3 elements of order 2. However, not exactly 4 elements. Why? Let G be an abelian group with exactly 4 elements of order 2. That means we are supposing that such a group exists, and we will try to derive a contradiction. By exercise, what was that exercise? 329. Order of A inverse is also 2, like that order of C inverse is also 2. So we must have, now because it's given that these are the only 4 elements of order 2, so these inverses must appear here because they also have order 2. So without losing generality, let us assume that B is A inverse and D is C inverse. Now since G is abelian, what happens if we calculate AC square? It is AC, but because it is abelian, the group is abelian, so in place of CA you can write AC. So A square, C square. Now A and C both are of order 2, so their squares equal identity, so this is equal to identity. So AC square is identity, thus the order of AC, again by just like this one, divides 2, and so this is either 1 or it is 2. if this order is 1, then it has to be the identity, because in any group the identity element is the only element of order 1. But then A is equal to, for example, C inverse, and C inverse is D, a contradiction. What is being contradicted? Our assumption that A, B, C and D are 4 elements of order 2 in the group, so they are distinct. But here we find that A is equal to D. So that means the order of AC cannot be 1. This case cannot arise. If, however, the order of AC is 2, then it must be one of these 4, because they are the only elements of order 2. So that means AC will have to belong to this set. Now again we will have contradiction. Let me show you why. If AC is equal to A, then by the cancellation laws in the group, you can cancel A from both sides and you will have C equal to E. But if C is E, then C inverse is also equal to E, which is equal to C, and C inverse, let me write like this, C inverse is D. But then again a similar contradiction has arisen, that C inverse is equal to C. So how are these 4 elements actually 4 elements? Because now they have become 3 elements. So this is a contradiction. These 2 clashing implication signs denote contradiction. So that means AC cannot be equal to A. Similarly, AC cannot be equal to C, because you will get a similar contradiction if you follow similar arguments, similar lines of thought. And if AC is equal to A inverse, say, then what happens? If you pre-multiply on both sides by A, you get A square C equal to E, but A squared is E because A is of order 2, so EC is equal to E. This implies C is equal to E. But if C is E, again you get that contradiction that D is equal to C inverse, then is also E, and that is also equal to C, so you get a collapse. So how can you have 4 elements? And similarly, you cannot have AC equal to C inverse either, because then you will have the contradiction that A is E. So that means this cannot happen. And if this cannot happen, then this condition also does not arise. So neither this happens nor this happens. That means something must be false before that, and that false thing is our original supposition that there are exactly 4 elements of order 2. So the group cannot have precisely 4 elements of order 2. And now finally there is one more. And with this set of exercises will be over. Over in the sense we have that exercise that I left to you, except that the others we have either completed or we have provided ample hints. Now this last one, suppose that G is a group in which every element has order 1 or 2, show that G must be abelian. Here also elaborate solution you will write. I will just give you the idea. Now in any group, I have been saying this again and again, I am repeating, the identity element is the only element of order 1. So the condition that they have given translates into this, that every non-identity element of G has order 2, and no non-identity element can have order 1. Now you want to prove that if A and B are any elements in G, then AB is equal to BA. Now in doing that, if at least one of A or B is identity itself, then the job is extra easy. Why? Because for example, if A is identity, then you want to prove that EB is equal to BE. But that is true, and that comes from the third axiom itself, which says that both of them will be equal to B, existence of identity. And if both of them are identity, then there is no, in fact you don't have any different AB and BA. They are actually the same product. So you can assume that both A and B are non-identity elements. So that case is only left to you. And in that case, both of them, because of this condition, must have order 2. So A square is identity, B square is also identity. Now what does that give you? It gives you these equations. A square is A inverse and B square is B inverse. So if you want to prove that AB is BA, you just use these relations. AB is A inverse B inverse. Now by an elementary group theory property, A inverse B inverse is BA whole inverse. Okay. Now what I am going to write here is BA. You will ask why, and the answer is that this BA may itself be identity. Even when A and B are not identity, BA can be identity, and that will happen precisely when B and A are inverses of each other. If this BA is identity, then its inverse is of course itself, that is BA, and if this BA is not identity, then this BA is an element like A and B. So BA square is also equal to E, and from there again you get BA inverse equal to BA. So AB is equal to BA. So any two elements of the group commute, and so G is abelian. This completes the current solution, and it also completes this set of exercises. So in the next Lee exercise video. We will prove that one which I left to you today. You please try to do that, and we will solve the other exercises that are going to come next. And tomorrow we have our usual real analysis. So that will be all for tonight. So if you want to say something about these things, you can write in the comment section below, and the usual blah blah blah. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.